A box with a square base and open top must have a volume of 42,592 cubic centimeters. We want to find the dimensions of the box that will minimize the amount of material used, which means we want to minimize the surface area of the box. Looking at our diagram, since our box has a square base, the length of this edge and this edge would be the same. So if we label this x, this would also be x. Let's go and label the height of the box y. Since the volume of a box is equal to the length times the width times the height, the volume of this box would be x times y, or x squared y. So we know that v must equal x squared y, which in this case must be 42,592 cubic centimeters. Because this equation must be true, we call this the constraint. Now we also need an equation for the surface area so that we can minimize that equation. The surface area would be the sum of the area of each face, and since our box has an open top, our box has 5 faces, the bottom and the 4 sides. Well, the area of the bottom would be x times x, or x squared, and then notice that the area of each face would be x times y, and since there's 4 of them, we have plus 4xy. This is the equation that we want to minimize. But to do this, we need to write s in terms of one variable, and right now it's written in terms of x and y. So if we solve the constraint for y, we can perform a substitution for y in the surface area formula, and then we'll have s in terms of x. So looking at our volume formula, or our constraint, if we solve this equation for y, we would divide both sides by x squared. Therefore, y is equal to 42,592 divided by x squared. So we can replace y in the surface area formula with this quotient. So we'd have s equals x squared plus 4x times this quotient here, 42,592 divided by x squared. Let's go ahead and simplify this. If we take a look at the x's, one factor of x will simplify out. This would simplify to 1. This would simplify to x to the first. And 4 times 42,592 is 170,368. And if we move this x to the first up to the numerator, it would be x to the power of negative 1. Now to minimize this, we'll use calculus techniques. So we'll find the first derivative, determine where it's undefined or equal to 0 to find our critical numbers. So s prime is going to be equal to 2x. Here we're going to multiply by negative 1, so we'll have negative 170,368. Subtract 1 from the exponent, that will give us x to the power of negative 2. We want to know when this is equal to 0 or undefined. Let's go ahead and write this as 2x minus 170,368 divided by x to the second equals 0. Notice how this would be undefined when x equals 0, but x can't equal 0, otherwise this length here would be 0. So let's go ahead and solve this equation for x on the next slide. Let's go ahead and clear the fraction by multiplying both sides of the equation by x squared. So we'd have 2x to the third. Notice here the x squared would simplify out, so we have minus 170,368 equals 0. Let's go ahead and isolate x cubed, so we'll add this constant to both sides. Divide both sides by 2. So we have x cubed equals 85,184. And now we'll cube root both sides in order to solve for x. This comes out nicely to x equals 44. So we only have one critical number, so we probably would be correct to assume this x value will minimize the surface area formula. To be completely sure, let's go ahead and use the second derivative test. So remember, the first derivative was equal to 2x minus 170,368 368x to the power of negative 2. So to find the second derivative, we'll find the derivative of the derivative. The derivative of 2x would be 2. Now for the next term, we're going to multiply by negative 2. So that'll be plus 340,736x to the power of negative 2 minus 1 is negative 3. Let's go ahead and write this using a positive exponent. So s double prime is equal to 2 plus 340,736 divided by x cubed. And now if we find the sign of the second derivative at x equals 44, we can determine whether the function is concave up or down, and therefore verify whether we have a minimum or maximum at x equals 44. So this would be equal to 2 plus 340,736 divided by 44 cubed. Notice how this sum is going to be positive or greater than 0, which means our surface area function, s of x, is concave up at x equals 44. So if the function is concave up at x equals 44, it would look something like this, and therefore at x equals 44, we know we have a minimum function value. So now if we go back and take a look at our figure for a moment, our goal is to find the dimensions of the box that will minimize the surface area. So we know our box must be 44 centimeters by 44 centimeters by y centimeters. So we still have to find the value of y, and we can find y using this equation here. Y is equal to 42,592 divided by x squared when x is 44. Already found this value, y is equal to 22. So to answer the questions, dimensions of the box that would minimize the surface area with a volume of 42,592 cubic centimeters would be 44 centimeters by 44 centimeters by 22 centimeters. To verify this, let's take a look at the graph of the surface area formula once we had it in terms of x. Here's the surface area formula that we used. Notice if we graph this, here's the location of a minimum value for the surface area. Notice the x value does appear to be 44. Notice the y value would actually be what that minimum surface area would be. So let's go ahead and substitute 44 for x to verify that this surface area is less than 6,000 cubic centimeters. We weren't actually asked to find this, but the surface area of that box would be equal to x squared plus 170,368 divided by x. So if x is equal to 44, this value comes out to 5,808 cubic centimeters, which again is verified by our graph. Hope you found this explanation helpful.